Let me start thanking, of course, the organizer for this conference, for giving me the opportunity to be here and giving a talk. And also I would like to thank very much the organizing of the program, What's Particle Theory, which has been just amazing. So I really want to say it because probably the best workshop I've ever been. Great people, great discussions, and it's been really lovely to be here. And in fact, I'm going to talk about something that so I started doing here like 2 months ago when Alex Pomaroli, also my student Marcello Romano, visited, and we started discussing together. We came up about this project here, which is revolves around this simple question that basically this question arises from the simple observation we never observe high-spin particle at the bottom of the spectrum. So we wonder why is the case. Is this a general feature or specific to particular theories we are looking at? So we wonder, can a massive high-spin particle be at the bottom of the spectrum alone, or what does it take for this to happen? So I imagine a situation like this, a spin bigger than 3½ some massive particle, but parametrically separated from the rest. Is this possible? If I tune this question to this audience, you should ask, can I vary the number of colors? Can I change the gauge group? Can I change the flavor, the representation? What does it take to bring down the low-lying mode to be high-spin particles? And so let me give you the punchline. So it's not possible. Okay? This is basically, if you want to take a message home, is this. And I'm going to explain that this talk is about why it's not possible, and or how you should change the infrared here in order to make it possible. And this goes under certain qualifications. Of course, I said I'm talking about massive particles, which I'm going to assume a parametric separation from the rest, high spins, and I'm assuming they are weakly coupled at the mass. And there is a range when I'm able to do calculation in the deep IR. The theory here from above can be strongly coupled, but I'm going to assume that the theory is weakly coupled in some range here.
Isn't in one flavor you see the electron variant and
Yeah, so in that theory is going to be strongly coupled at the mass, so that's the assumption. So in a sense, this is a bit of a summary of why this cannot be done, is because if you look at high-spin particles, they have a lot of polarizations, and many of them will make the amplitude grow very fast with energy within the IPhT theory. Okay? Within the range, if you have a gap between the new states within the IPhT theory, the amplitude will grow very fast. Even if it remains small, the energy growth, the rate is larger than 4. And this 4 is actually the boundary set by causality constraints. And that's why, in a sense, this theory cannot be realized, as I will explain in the following slides. And this also, I want to stress, has nothing to do with the size of the coupling. This is really about, you see, all the bounds I'm going to show that relate to this fact are about ratios of couplings that are completely projective. And this has to do with the free theory itself is on the verge of being consistent. If you have a theory which is free from massless particle, it propagates on light cone, and if you turned on a tiny coupling with the wrong sign, coming from opposite, it would allow you to propagate outside the light cone, even if it's a tiny coupling that you generate by turning on some backgrounds, and this will allow you to create a causal paradox. So it's not really about size of coupling, it's about causal properties of the theory. Of course, we know that high spin can arise at the bottom of the spectrum under certain conditions, and this requires to change the IPhT theory a little bit, adding more particles. For example, of course, if you add gravity, in supergravity, you have a spin 3½ particle at the bottom of the spectrum. So I will show you what are the options and why certain things are possible, others are not. So this is, of course, part of a broader picture, a broader set of questions, how you can determine as a low-energy observer what is consistent in the infrared, what theories comes from apparent theory in the UV, along the energy flow, you flow to some particular point here. How can you tell this boundary? Is here a low-energy observer. So you need something that tracks the properties of the energy flow from the UV to the IR, and the tool I'm going to use is this very old method, the special relations, combined with the modern understanding of effective field theories. So causality here is basically the statement that you have some control of the analytic structure of the amplitude. Okay, this is what provides the link along the energy flow from the UV to the IR. So you know, for example, in the 2-to-2 scattering, that's what I'm going to consider, the amplitude is analytic in certain region. This is, for example, in the Mandelstam S-plane, a fixed momentum exchange. You have some analytic region, well, everywhere except, for example, in this case, if I focus in the forward scattering on the physical S and U channel branch cuts. And therefore, any information that I gathered by integrating my amplitude in the infrared here, which pick up information about the effective theory, I can relate it by deforming this contour by integration along the discontinuity that go all the way to infinity. But of course, I cannot use the effective theory, but I can use some broad property of the amplitude that I know must be true. So let me look at this paradigmatic example of pi-pi scattering at zero momentum transfer. So you consider an amplitude, I do a contour here divided by some powers of the Mandelstam. I'm going to refer this like an arc, which is this circle here. This is going to be in the infrared, so it's something you can calculate with effective theory. Remember, I'm assuming there is a gap to the new states, so I'm able to do calculations there. This is going to be a linear combination of widths of coefficients, it's something that I can control. And this particular setting, it picks one at a time. Because of causality is also the same as an integral that extends all the way to infinity of a discontinuity, which I don't know what it is in general, except it's positive because of unitarity. So this means that this is basically a moment with respect to the positive measure given by the optical theorem here, moment in the 1/s variable. So my widths of coefficient are just positive moments of a distribution. And this already gives a lot of information, in fact. So this is a schematic picture, the way you can extract this information. You have some of these arcs, which are in one-to-one correspondence with widths of coefficients, up to rescaling some mass dimension that are integral over some positive measure for some moment. That is certainly positive, that justifies the name positivity bound. But once you have a positive measure, you can test it. You can test it against some positive functions. Of course, there are bases of positive functions, for example, Bernstein polynomials and so on. For example, this one you integrate against 1 minus x squared, which is positive in this interval, you immediately get that two consecutive widths of coefficient here are monotonically, so the series of widths of coefficients is monotonically decreasing, which is very interesting, starting from the first one for which the special relation was convergent, which is the s squared coefficient, the e to the fourth I was alluding before. That's the first where the dispersion is convergent. So starting from there, you learn information about the series, because they are moments. And you can turn this information around. You can extract an upper bound of where the new states have to appear if you measure two of these consecutive widths of coefficients. You can, play with this a little bit around. You can start integrating your positive measure against other polynomials with free parameters, and this will give you some nonlinear relation that this matrix of widths of coefficient must be positive definite. You can generalize also. Here, this simplified version was in the forward limit, but it definitely holds true beyond that. And you get that, for example, in a plane like this one, where the ratio 2 consecutive widths of coefficient, and the next one, you have to live in this wind-like shaped region, even though, for example, you could have imagined situations like a symmetry that would kill C4 relative to C6. So you could imagine engineer a symmetry, but you would live up here in the corner. Well, that theory with that symmetry, which looks natural because they have a symmetry to enforce it, would not be consistent with causality. Okay, so I'm saying this is something additional to the user constraints that come from symmetry arguments along energy flow. And the lesson here, well, of course, that not everything goes here. There's a structure among the Wilson coefficients. They are bounded, and moreover, they are always smaller, basically, that the leading, the first unsuppressed is going to be the e to the 4. It never happens a situation where e to the 4 is suppressed relative to the next ones. So this was a story for a scalar. So this raised these expectations. So if this carries through for particles with spin, then these theories are in trouble, because you may expect them that actually the leading term in the amplitude is going to go from very high powers of energy just because they contain a lot of helicity states, in particular zero helicity or the one helicity and so on, will grow very fast with energy. So I want to show that this indeed is the case. I want to focus on the simplest one, the one which has the boundary between low spin, high spin, the massive spin 3/2. In particular, the one that the polarization that will lead the story are the longitudinal polarization, the spin 1/2 inside. So this is the setting. So I'm imagining I have a gap between some new state and my effective theory made of just 4 degrees of freedom, the helicity plus minus 3/2, plus minus 1/2, and nothing in between. I can sit somewhere here in the middle, much above the mass of this particle, much below the rest. If I want to capture the low energy and leading contribution to the amplitude, I focus on the lowest dimensional operators, which are 3 of them, and they give rise, if I focus the longitudinal scattering, they give rise to an amplitude for the helicity minus 1/2, minus 1/2, plus 1/2, plus 1/2 of this form. And you have 3 free parameters that match to these 3 coefficients here, this one, and this one. Some linear combinations. But you see, this guy here is linearly dependent on the rest. It's just suppressed by basically power counting by one insertion of the mass. So that's precisely the tension. So this guy should be leading because his little group factor here is e squared. This is another e squared. This one should be leading. Based on the expectation I show you in the scalar case, actually it's going to be suppressed relative to the other. Notice there is nothing I can do about the overall size of the coupling. If I scale this coupling to small, nothing changes. The ratio of this guy over this one is always large. So in order to address this, let me use this this tool, which are TU symmetric dispersion relations, because the amplitude here is symmetric under exchange of TU, because I can exchange 1 and 2 here. And therefore, rather than dispersing in the Mandelstam S at fixed momentum transfer, it's rather convenient to disperse, keeping fixed this combination, TU over S. Okay, this P, in a sense, is a TU symmetric generalization of the momentum transfer. It's going to be convenient for the rest. There's a little bit of a complication because I introduced new discontinuity in the problem. At least it seems so, because the relation between the momentum transfer square and this variable here introduce some branch cut and run it between 2 branch points. To be careful when I run my dispersive argument, which path I take for moving from, for example, physical S channel to the U channel. I like to specify which path I'm taking. But in fact, it's not really an issue in the end, because crossing or not, this square root here amounts only to exchanging T and U, and this amplitude is TU symmetric. Actually, at the end of the day, this was just red herrings. And notice that this variable also, I can work in the Regis scaling limit when I deform my contour to run this dispersive argument contribution at infinity. I was dropping it because I was in this regime, which is kept working also with these variables. So I can basically repeat the story that I had for the scalar theory for this spin 3/2 particle scattering. A fixed P, this generalization of the momentum transfer in a certain range to ensure analyticity. So again, the whole point of this is that I have some rule that match what I know or I'm able to calculate the infrared with the unknown but positive discontinuity integrated in the UV. So this is what we get. We get that on the infrared side, we get a fixed order polynomial in this generalization of the momentum transfer, we call it P. Whereas on the right-hand side is a linear combinations of a 2D moment problem now. So because I'm working a finite momentum transfer, therefore my imaginary part is function of two variables, which is the energy of the system S, and also the angular momentum if expanding partial waves. So they measure a support on a two-dimensional support, which is integers in spins and continuums in S. So it's a two-dimensional moment problem, basically I'm solving. I'm matching and saying that this particular combination with the coefficient for any value of this momentum transfer generalization of is equal to these particular combinations of 2D moments. And these moments are resum in particular polynomials, which are polynomials, in this case a Legendre polynomial and a Jacobi polynomial, because of the helicity selection rules. And therefore, this is true for any P, for any momentum transfer. So I can get a sum rule here between all the Wilson coefficients of the Eigen-spin theory and the moment of the UV theory. So for example, C10 is just the sum, or minus C1 is the sum of the moments with the lowest moment, then C20 is the difference of the next moment, and so on. And this allows us to get relation among them. As I was saying, knowing that they are moments basically buys you a geometric structure where these Wilson coefficients have to live. For example, C20 here, which is the coefficient of is the first coefficient of e to the 6, is actually bounded by C10, the coefficient of e to the 4th, because I just take the norm of this guy, it's going to be bounded by the norm of this guy, so it immediately gives you this hierarchy. Okay, never possible that C21 exceed this range in units of the gap to the theory. C21 here, which is the other e to the 6th term in the Feti theory, is also bounded because you have a linear relation that's true for any P, and C21 is controlling the slope of a function, which is linear, whereas this function here is bounded above and below. So you get this slope here cannot be arbitrarily high in one direction or the other. This gives a bound on this ratio, C21 over C10 shouldn't be 2 and 6. So here this manifests the contradiction. Having a low lying 3/2 particle and nothing else with a gap, the prediction for that is that this ratio is actually larger and larger the more I push the gap, whereas causality demands this to be order 1. I can never push capital M, the gap to the new states, to be parametrically larger than little m. So what are the lessons here? So spin 3/2 alone is consistent with causality. The issue, as I was saying, is that the leading growth in the Feti theory has to start with e to the 4th, nothing to do with size of couplings. And of course, this is generalized to eigenspins, nothing specific to the spin 3/2. Just in fact, eigenspin, eigen 3/2 makes the problem worse. And this is another example that we looked at a couple of years ago for spin 2, massive gravity, just run exactly basically the same argument. You get that new states must be really around the mass of the gravity, which of course experimentally is like 10 to the minus 32 electron volt, which is the size of basically Hubble scales, this stringent. So what about changing the theory? What about how can so let's imagine I insist in having a high spin state at the bottom of the spectrum. What does it take to make it compatible with causality? So I need to change the Feti theory. I need to add new degrees of freedom. Okay? That's the only way. And so if I try to add the spin 1, it's not going to work, simply because I was working with a Majorana spin 3/2. There's no charge. This guy can couple to neither dipole. And the coupling is very higher dimension, will make it worse. So this is not going to work. A scalar may in principle work. there's a coupling that could dominate over the contact term of the spin 3/2, but it turns out that if you run the calculation, actually it makes the e to the 4th term leading, but with the wrong sign. So it also would be an issue with causality. So the only other option with low spin states that you can add is one with the graviton, which is good news because it's the only one we knew. So in fact, this argument, I'm going to show you in a second, singles out supergravity as the only option for the case of spin 3/2. So let's see what it changes. So what it changes is that you have a new operator in the effective theory, the coupling to the stress tensor of a graviton that can be exchanged. And now if you look at the scattering longitudinal, in addition to the contact term from the spin 3/2, now you have the exchange of the graviton. Of course, if the theory of the spin 3/2 has nothing to do with gravity, say you imagine it comes from a gauge theory, the result was the same as before. These two scales are completely different. E to the 6 will be dominating, and you have issue with causality. So the only way, when you tune this scale to be the same, you can arrange a cancellation or suppression of this one. And this is precisely when all these contact terms actually has gravitational in size. So this really points towards a gravitational theory as a unique solution for putting down a spin 3/2 particle. So there's no gauge theory that would do that. Okay? You need to add the graviton and tune it to be gravitational in size, all couplings. Once this is done, you land on e to the 4th term as leading contribution, and this comes nicely with the right positive coefficient. If you want to analyze further this theory, at this point, once the graviton exchange has done its job, you can take a simplifying limit where you decouple now gravity, while keeping the spin 3/2 particle lights and its mass to 0, keeping this ratio fixed. So it will decouple this contribution, we'll keep this one. And you recognize just the theory of Gorstini. In this case, this is the limit of rigid SUSY. And you discover also the usual relation between the mass, the SUSY breaking scale, and the Planck scale. It's completely fixed by causality. Okay? There's nothing, you cannot play around it in flat space. So once you land there, so now you can study, for example, the theory of Gorstini on its own. So you decouple gravity, it did the job, it fixed the theory of the spin 3/2. Now you can look at the theory of the 1/2 in isolation. Forget about what you got there, just to study the theory of Agostino, so the particle at the bottom of the spectrum after SUSY breaking, and see what you get. So this is the projection of the space, the effective filtration, so the space of Wilson coefficient considered with causality projected on this two-dimensional plane, the leading to Wilson coefficient normalized to the e to the 4th one. You have to live inside this region. Since it's a convex space, this is determined, everything inside is determined by linear combination of things at the boundary. And so it's determined by the kinks or corners that you see. And there are very simple familiar theories here. For example, this one is an exchange of a spin 0 particle in S channel, or Rafferty model of SUSY breaking. This one would be this one is exchange of spin 1 particle in TU channel. And you correspond to a Fayet-Leopoulos type, and you can dial from one to the other by changing how much D breaking or F breaking supersymmetry you have in the system. So these are were expected, so no surprise here. So more interesting is this side here. There are two more corners. And one we have been able to identify is interesting because it has poles at the same mass in two different channels, U and T, simultaneously. That means that at the same mass, you're exchanging infinitely many eigenspin. So that's the UV completion of this amplitude, which doesn't look like very local or doesn't seem something arising from quantum field theory, but it's sort of a Regge-like trajectory that you slope against arbitrary vertical. And there is another one here which we haven't quite yet identified, except that this morning I got an email from Francesco Ciotti, one of the young collaborators. Maybe I know what it is. He showed me a formula here, so I didn't check it myself. So I like as a tripole pole there, like U, T, and S with poles at the same location, square, and there are infinite towers, eigenspin, both in the plus helicity or plus minus channel, in this channel or in this channel. Anyway, to be checked. And there's an interesting region here in gray, in this space of Agostini, which comes from this concept of null constraints. Not only the dispersion relation gives you some rules for the Wilson coefficient of the effective theory, but gives you also a relation among the spins in the UV theory, which is this one, okay? So there are combination of moments between different spins that sum up to 0, not a Wilson coefficient. There's a relation among them. And this theory here trivialize them, because you see L equals 0, L equals 1, and J squared is the Casimir, is L times L plus 1, trivialize all these sum rules. So if I remove the trivial solutions, I ask, what is the space allowed by non-trivial solutions? Is this region here, and there is where you need infinitely many states exchange. Okay, so it's not clear, at least to my knowledge, what kind of model of SUSY breaking calculable will produce that. Okay, of course, it could be some, model of SUSY breaking from strong dynamics, but then to extract the spectrum from that is very hard. So I wasn't able to match to any concrete model of SUSY breaking. All right, so let me get to conclusions. So we have never seen massive eigenspins at the bottom of the spectrum, and well, there's a good reason for it. It's causality, okay? That's the reason. And in certain cases, for the case of spin hard, for example, you can fix it, but it's a unique fix, okay? That's really specific. You need to, in this case, you have to make the theory gravitational. It's not that you're going to play with your gauge theory, dial any parameter you have there, and hope to get a light spin half of the spectrum. But that's not going to give you also gravity, for sure. So it's really a different type of theories. And also, I showed that with the same type of reasoning, you can explore effective field theory either for the Agostini, okay, for spin 1/2 particles. Now, there's an interesting twist in the story, which we started this soon, so we are still confused about it. Is the case where, let's imagine we have more degrees of freedom in infrared. Let's make it a Dirac spin 3/2. So we double the degrees of freedom. Now you can couple also to a vector. No, that's and it seems. So we are finding, to our surprise, that it seems to exist solutions that don't require gravity in order for this theory to be causal. And so we don't know. So I think it's fair to say we have to think carefully about this. So without appealing to gravity, it seems that we are able to find a solution, all causality constraints, coupling a spin Dirac 3/2 to a vector. But it's really preliminary. The other thing I want to mention is the following, that so usually when we discuss positivity bounds, we can bound very relevant operators, like things that start with the energy to the fourth in the amplitude and higher. So we never are able to probe things which are the lowest dimension, the thing you see first, for example, colliders. For example, G-2, typically you are not able to say anything most of the time. So now, for eigenspin, this story is slightly different, because G-2 is still a dimension 5, but since you have a lot of helicity, the amplitude will grow very fast with energy, so you are maybe able to probe it also with the positivity bound and see whether you can pin it to which particular direction you can go, or under what condition you can go in one direction rather than in another. And then, of course, what we would like to do is to understand better the space of effective theory for Agostini and see which kind of theories lies at the boundary. Thank you very much.
Thanks a lot, Brando. I have a question over here.
Thanks. Just to follow, about this 3/2 in isolation. I'm just trying to follow your point that you have kind of behavior which is energy in high power, right? And then at large energy, trying to go to the very large energy to be like a square or something like that. But no, what I have in mind is, let's say that we have kind of theory like QCD, where, not specifically QCD, but just an example that the theory which provides you with a good asymptotic behavior, and of course I understand that then you have this 3/2, and then you would have kind of excitation for this with the same spin, but it would be this distance, but no, of course QCD it would be just characteristic lambda, whatever QCD, the scale, but generically I can think that the scale could be different, right? I mean, because it depends by the size of this composite object, right? So the 3/2 is composite. What is the size? Then the size will tell me what will be the next excitation. So I mean, how to say isolation, not isolation, depending on this particular gap, the scale which is associated with the intrinsic compositeness of the 3/2.
Yes, so it's true. So I mean, we basically get concrete upper bounds on this isolation scale. Oh, sorry, too much. So for example, you can see here, you can read this as, take the norm of this. So this provides an upper bound of separated the scale can be. It's given by the ratio of this Wilson coefficient. They just say that this is incompatible to make it very large. It's order 1. So what you see in QCD, if you want another way to phrase it, is what you see in QCD is generic. So you cannot separate parametrically more the mass of that state from the next. That's a generic situation. In a gauge theory, for the spin 3/2, you never can get around that. That's the message.
So in this way, it's numerical. You have a numerical limit.
Yeah. For example, another example is this one. For a spin 2, the numerical value is 28. Okay. So concrete number. So how much can I separate my low-lying mode from the next? Not much, no matter what you do.
But then it's the limit for the structure of the, in a sense.
The structure?
But at the same time, it gives you the characteristic size of compositeness.
Yeah, if you want this one, you can say is yeah. I think you can interpret this one. Yeah.
Maybe I can ask one question before we go on, which is you have this picture where there are no discontinuities until you hit capital M. But of course, there are these light particles and they're rescattering. You say it's weak coupling, so the discontinuities are very weak. But don't they blow up and kind of turn on, with scale instead of abruptly at one scale M? And how do you handle that?
There are two comments on this. So so maybe let me show you. So first of all, for example, if you look, so here I was carefully projecting on the lowest Wilson coefficient, which are the least sensitive to this. In fact, these, for example, don't even run. So whatever contribution from the IR loops for running just doesn't enter in this one, and projecting on those, this is one of the reasons. The other thing that I have here in the backup slides is that, in fact, any theory which has suppressed e to the 4th, so let's take this case, I have a series of terms starting from e to the 6th, for example, I have a suppressed e to the 4th, necessarily must have a small coupling. So the fact is very simple to see because you can write a dispersion for this term here. And this is actually larger, this is an exact inequality, larger the contribution in the infrared. So now I throw away the UV, just look at it's larger the contribution in the infrared, but infrared is given by this coupling squared times 16 pi squared. So I get the epsilon should be actually larger than something. So the coupling constant here is actually bounded by epsilon. So if this is suppressed, the coupling constant cannot be large at the scale of the new states. So it's completely under control. And if you look, for example, the math here for the spin 2 case, you get that the coupling at the scale of the new state is 10 to minus 30, which is very small.
Thanks. Over here.
Is there any connection with Weinberg-Witten theorem?
Not really. Not really. I mean, so
If we parametrically make small m to be smaller and smaller, and we in the end getting massless spin, higher spin particles, then Weinberg-Witten.
Yeah. So the point is that m equals 0 and m epsilon is a discontinuous jump. You go from 2 degrees of freedom to 4, for example, the spin 3 half. And what was driving the physics here was exactly the degree of freedom. They are completely blind, the Weinberg-Witten, where the longitudinal, which they have a matrix element with mu nu, which is non-vanished. Instead, the transverse here were completely healthy. So I would say no, there's no link. It's not adding a mass to higher spin is not a small deformation. It's order 1 deformation.
So I have to ask, what about j equals 1, though? We don't have a massive vector that's not free.
So j equal 1 is low spin. So j equal 1 satisfies everything here because the leading amplitude doesn't grow faster than e to the 4th. It grows lower. So it's, yeah. So there's nothing, in a sense, it doesn't have...
Do we have a good theory for that? Of an isolated vector that's interacting?
I mean, like theory of a photon.
That's free. That's free. Interacting one.
No, I'm saying, imagine. No, it's not interacting. I mean, it's free in the deep IR, but it's not free at generic energy.
So you want f to the 4th interaction of photons or something?
F to the 4th interaction is good. E to the 4th is good. So integrate out the electron.
Okay.
I mean, standard model, integrate out everything all the way up to nothing is left but the photon.
Okay.
There you go. So that theory is good.
So I have a question. So now, if you include the graviton, now you have the graviton pole, and if you don't consider the decoupling limit, you have to measure the Wilson coefficient in the finite impact parameter to get some bounds. Do you have that those constraints?
So indeed, so you are totally right. So this one, you see T, so impact parameter T negative, which I was using basically here, provides a positivity for S squared. So you may perhaps thinking of relaxing some positivity from the other contribution.
Yeah.
And I mean, that's exactly why we took this limit, because this remains a little bit of an open problem at the moment. In 4 dimensions, which are where I focus.
But you can just get some bounds in terms of the logarithmic divergence, right?
Yeah, which is a divergent bound. And I mean, as you know very well, because you contribute to this. Yeah, so I don't have to say, I wanted to avoid IR divergences.
I see.
So that's exactly why I took this limit. I see. But I think it should be a way to make the bound robust also in 4 dimension, including gravity. Okay? I think there was a recent paper by Julio Para-Martinez where he's making a progress on one side, making the bound IR finite, but it's very, very weak bound. So I think there is much room to improvement. Yeah.
No, just continuing to last questions. Say, J equal 1. Let's take kind of an Romisan, so not abelian J equal 1, but non-abelian J equal 1. There it would be.
I mean, let's take electroweak theory.
Sorry?
Electroweak theory. Spin 1.
Without the Higgs, right?
Well, integrate out the Higgs, imagine Higgs is heavy.
Higgs-less
theory where you integrate out the Higgs and you just add
but it's
that's consistent.
Different type of growth because, say, annihilation into say 2 row meson is okay, creation is 3 row meson would be growing, and 4 meson growing even more because of longitudinal polarization. Right?
Yes.
And then I think that maybe you can apply this kind of limits for this situation as well. So for
not really. So since I mean, so the leading term in that case would be E squared. Now, if you target constraining e to the 4th, which is subleading to that, it becomes more difficult. Okay, that yeah, in principle, there are various issues, but it's possible.
But it starts from 3 row meson, not before 2 loops, and not before 2 loops, right?
Yeah, or there is also or there is an eigenvalue term you can write down, which starts at 311. Yeah, it's possible. It's possible doing it. Just not the leading term. So you are fighting against the loops of the leading. So you learn much less.
Okay.
Are there other questions for Brando? All right, if not, it's time for lunch in the courtyard, and we'll meet back here at 1:45 for Anna Hasenpratz's talk. Thanks again, Brando.